Recording.
So, hey guys, we're group two, and my name is Sabag Momjan, and for
I'm
our
David Dupay.
project, we're going to be doing, we're going to be selecting the correct material for a submersible capsule. Just a brief overview. So, a submersible capsule, or a submersible in general, is basically a submarine, but it's mainly used for research purposes. It'll just go down to like really low depths within the ocean and then back up like fairly quickly whenever we need it for research. And we want to focus on the capsule of the submersible, so where the person is going to be held in. And this capsule is essentially what the person is in, and it's used to store various like electronic materials. And the goal of this capsule, and when selecting the materials, to minimize our mass, so we can get put more equipment into our submersible. And to minimize, and when okay, so we want to minimize mass, and we also want to maximize our yield strength. This ended up we ended up getting a material index where we had our yield strength over our density was our material index. And after going through the Ashby material selection process, we find that nitronic 50 stainless steel was the best material for a submersible capsule because it has really low density, a great yield strength, and it has very good corrosion resistance within the ocean, so it won't corrode. Just a quick, brief overview. So we found that the dimensions of our submersible capsule should be a diameter of 54.5 centimeters of our capsule specifically. And this is what previous capsules had in terms of their dimension. But we can have a thickness of 3.21 centimeters, which is in fact half of what previous capsules' thicknesses have been.
All right, some quick background. You already mentioned the submersible. You can see the original dimensions of the submersible there, but the most commonly used material historically for creating submarines were steel, due to their properties of dense, shape-forming, malleable, non-corrosive, and like lightweight. The past specific submarines during, let's say, a wartime era, I would estimate like Cold War, would use AHY-80 steel, and that was processed using open hearth or electric furnace process, to which you turn to a grain, and then later on you mold it into whatever shape you want. And then there's a second step where you'd heat treat it and temper it to achieve the specific property. And on the right image, you'll see where we'll be focusing on. All right, next one.
Oh, wait, my bad. Wait, where'd it go? Did I just stop sharing?
I think your screen
It's still sharing, but you got out full screen.
There you go. All right.
All right.
And then a little more literature review on stainless steel, which uses the furnace process, form and desired shape, which is then, processed again through tempering on the second step with heat treatment. And afterwards, you would descale it, cut in desired shape. For the metallurgy, you just, you can adjust a little bit of the structure by adding different stuff to change the composition, which lets us control the grain size. And you'll see that when we add nitrogen on the net, like later on down the line, it does something like really cool.
All right, so I'm gonna go real quickly through our process selection. So for our submersible, we're only making really one pressure vessel. So our batch size will be one. Our shape is a three-dimensional hollow sphere. We're gonna have an outer diameter of 4.5 centimeters, a thickness of 3.21 centimeters. Our material is nitronic 50 XM19, and we want a tolerance of less than 0.1 millimeters. As far as process screening, because our batch size is only one, the only suitable way we can manufacture our machining, and the reason why we couldn't use sand casting is because when you sand cast our nitronic 50, it decreases our yield strength. And we want to optimize how strong our nitronic 50 is. And so essentially, what we'll end up getting is a block from the manufacturers, which will then use conventional machining to weather away into a semi-spherical shape. So from this block, we'll get two semi-spherical shapes, so two semispheres, and then we'll wheel them together using plasma wielding. And for finishing, the only viable method to do this with is through polishing, because yet again, our batch size is one.
materials analysis. Okay, so I mentioned before that we added nitrogen to it. It does something really cool. So with an increased nitrogen concentration in our composition, it leads to overall higher strength, corrosion resistance, and toughness when contrasted to traditional stainless steel. But the really, really cool thing about it is that during the welding step, it helps suppress carbide precipitation, which is basically when we're welding, there's a chance that we might introduce, well, carbide, and then that would maybe introduce like cracks, which, you know, it's really bad down the line because we're making pressurized vessel. So overall, N50 steel has proved to be like really, really good for submarine vessels.
So this is the cost analysis part. So since we wanted an outer diameter of 54.5, we want a 54.5 cube with the length of 54.5, but we add 10 cm on each side in case of human error since we're only making one. So these are the numbers for the cost per unit mass and the density. And then after doing the calculations, cost per unit mass is 13,000. And these are the costs of the tools that we need to use it. The saws for cutting, the plasma wielder for binding the two halves together, and then the buffer for the finishing. So overall, our total cost came up to around 16,000. And after some research, we found that the sphere needs to last around 5,000 cycles. So that gives us $3.2 per dive for the sphere capsule.
So now we're going to talk about the impact on the environment, and we're going to talk about the impact on the environment in three regards. Firstly, we need to talk about the impact on people and understanding, the biggest issue when it comes to anything today is its impact on climate change and its emissions of greenhouse gases first and foremost. So initially we see that there is this proportion of the tonnage produced by the manufacturing of our steel and the processing our steel in proportion to the weight of our steel. So if you consider the initial mass and in conjunction with the added weight of any equipment that we may use, we see that we have a potential steel weight around 12 tons, which amounts to around 15 tons of CO2 emitted. However, we do have the benefit that we are not like a military submarine. We are not running on diesel or nuclear, so there is no concern for large-scale waste because this vehicle most likely will be operated with a lithium-ion battery and a series of simple motorized thrusters. Next is our impact on people, impact on the planet. So obviously we have the carbon footprint, but we also have to reconcile the impact on the environments that this vehicle will be going into. Because the submersible is a deep sea vehicle, it is going to be going to fairly isolated biological environments, which means that there is a large chance that we could be introducing or moving an invasive species. In particular, several papers have found that there is the possibility for specific archaea or other small organisms that are living near volcanic vents and other highly biologically active areas that are being researched to be transferred. So it's important that we have the consideration that if our outer material is not capable of not impacting the environment, but not allowing any attachment of organisms, there is a highly likely chance that we could be spreading very invasive organisms. Next, we can see that there is the impact on prosperity. So we are only doing a batch size of one, and we are using fairly common materials. So we aren't exactly causing the same level of impact as a mainstream auto manufacturer. However, with that said, we also have to take in consideration the impact on people and the economy as a whole, because we are actually using pre-manufactured tools. We are not creating tools of our own for this manufacturing process. And so we have to take into consideration supply chain logistics that might otherwise cause worsening of global exploitation. But overall, our vehicle is going to be fairly green. And that concludes our presentation. Thank you.